In part 2, we're going to start with question 5. Applicants for a pilot training program with a passenger airline are screened for color blindness. Past records show that the proportion of applicants identified as colorblind is 0.045. In question A, we have to write down a suitable model for distribution of number of applicants identified as colorblind from a total number of n applicants. Well, judging from this situation and with probability, and we have n applicants, it seems like we have binomial distribution. So you can write it as binomial distribution of n applicants with a probability of being colorblind, which is 0.045. In question B, state one assumption necessary for this distribution to be a suitable model for this situation. And since the probability of having colorblind is 0.045, so it doesn't change over the course, so you can just say that the probability is fixed. That is one assumption. Or you can just simply say that all applicants here, they are independent to each other. In question C, using a suitable approximation, find the probability that exactly 5 out of 120 applicants are identified as colorblind. First, we are going to define a random variable for the original binomial distribution. So we let x as the number of applicants from 120 of them. And we have 120, that is the total number of applicants, that is n, 120. And the probability that each of them will be colorblind is 0.045. So this is the original distribution. Next, we are going to find the suitable approximation. In this case, n is large, which is 120. And the probability is pretty small, which is 0.045. Or you can check NP. NP in this case is 120 times 0.045, which is 5.4. So it is less than 10. If NP is less than 10, N is large and P is small, we can use Poisson approximation. And then we are going to define a random variable for Poisson approximation. So let Y has Poisson lambda. And according to Poisson approximation, if you want to use Poisson to approximate binomial distribution, lambda will be NP, which is 5.4 here. So we can rewrite this as Poisson of 5.4. That's a distribution of the approximation. Now we can start to find the probability. So in this case, we have to find a probability that exactly 5 out of 120 that are colorblind. That means x is 5. And in this case, we're not going to find the probability of x is 5 directly from binomial distribution. So we have to use the approximation, which is Poisson approximation in this case. So we approximate it to be the probability of Poisson, which is y. And since Poisson distribution is a discrete random variable, and the binomial is also the discrete random variable, so you don't have to apply continuity correction. If you wanted to find the probability of x equals 5, then you can find the probability of y equals 5 right away. And now we're going to use Poisson formula for finding the probability, which is e to the power of minus lambda, which is 5.4, times lambda 5.4 to the power of 5 here, divided by 5 factorial. And the answer is 0.1728, and so on. So this is the probability of x equals 5, and now we can round it to 3 significant figures, which is 0.1723. That's the answer. Here in question D, explain why the approximation that you used in part C is appropriate. Well, like we discussed before, in this case, n is large and p is very small. That's why we use Poisson approximation. Next, Gemini claims that 75% of applicants for this training program go on to become pilots. From a random sample of 96 applicants for this training program, 67 go on to become pilots. Using a suitable approximation, test Gemini's claim at 5% significance level. State your hypothesis clearly. Okay, first let's see what information do we have here. The claim is like 75% of all applicants, they're going to be pilots. That's a probability. We have this probability here, which is 0.75, and a sample of 96, so that is n. That means we have binomial distribution. So we can have binomial distribution of 96 and 0.75. Okay, let's define the random variable for this distribution. Maybe we use v. Okay, so the random variable v has binomial distribution. Now let's see, the question said you gotta use the suitable approximation, so you can't find a probability from binomial distribution. So let's see what kind of approximation we are going to use here. N is 96, so N is large, and P is 0.75, which is not very small. But we can check NP again, which is 96 times 0.75. It is 72, which is way more than 10. So in this case, we can't use Poisson approximation. So without Poisson distribution, we just have to use normal approximation. To use normal approximation to approximate binomial distribution, we have to find mu and variance here. So mu can be found by using NP, which is 72 in this case, and variance is NP times 1 minus P, which is 72 by 1 minus 0.75, and the answer is 18. That's normal approximation. 72 and square root 18 squared, that's variance. Let this random variable as W. Next, let's define the hypothesis. In this case, we wanted to see if Gemini's claim is exactly 75% or not. So for H0, we're going to use probability equals 0.75. That means her claim for 75% is like exactly 75% or not. That means for alternative hypothesis, we're going to use not equal. Okay, so in this case, we have two-tailed test. So I'm going to draw this diagram first, and you can see that your random variable starts from 0 to 96. You will have critical region here and here. This part is the significance level. Since we have two critical regions, we have to divide significance level into two parts. Alpha equals 0.05 at each tail. The probability of the critical region will be 0.025. That is alpha over 2. This one is also 0.025. And then we wanted to check if 67, which is our test statistic in this case, we wanted to check if it's inside the critical region like this, or it is outside the critical region. Could be inside the critical region here or outside right here. Like, we don't really know for sure. But since we have binomial distribution, we know that the mean of binomial distribution is 72, because the mean of binomial distribution is NP. So right here is 72. And now our test statistic that we wanted to check is 67. So in this case, we better check the lower tail here. If 67 were to be inside the critical region at the lower tail, then the probability of V, which is our original random variable from binomial distribution, V less than 67, it has to be less than or equal 0.025. And V can be exactly at 67, right? So you can add like the equal sign here. This is the case when it is going to be inside the critical region. So now at the lower tail, we have to check if the probability of V less than or equals 67 is going to be less than or equals 0.025 or not. We're going to check that. Check the probability of V less than or equals 67. We use less than because it is the left area of 67. Well, in this case, we are not going to find a probability of V less than or equals 67 from binomial distribution right away. We have to find it from the approximation, which is normal approximation in this case. So we are going to approximate it to be the normal distribution variable, which is W. W is continuous random variable. So in continuous random variable, less than or equal, they're pretty much the same thing, so you can just write it as less than. And again, since W is continuous, so we gotta use continuity correction. And in discrete distribution, you can see that this whole bar represents 67 and this whole bar represents 66. So the area or the probability that we have to find the probability of less than or equals 67. That means we have to change this area, this one, and so on. So everything starts from this line. But in continuous random variable, this line is not called 67 because it is the line in between 67 and 68. In continuous random variable, this line is considered 67. The line in the middle of each bar, this one is 68 and this one is 66. So the line in between, like this line, that is 67.5. The region that we wanted start from 67.5 from continuous random variables perspective. So in this case, by applying continuity correction, W has to be less than 67.5. And now we are supposed to show working out, so we have to change from W, which is normal distribution, we're going to change it to standard normal distribution. We're going to define z. Here z has normal distribution 0, 1. Change it to the probability of z less than. Okay, so we're going to transform this to z by using this formula. Z equals your current random variable, which is w, minus mu divided by sigma. 67.5 minus 72 divided by square root 18. And then we calculate this part. Z less than negative 1.06066 and so on. Then we are going to use a calculator to calculate this. If you draw the diagram here, that is when z equals 0. And this is when z equals negative 1.06. I'm going to find this probability. So from calculator, by using normal CD, we can see that we changed everything to standard normal. So everything starts from negative infinity. That's a lower bound. For lower bound, you use negative infinity is like minus 9 times 10 to the power of 99. And the upper bound here is, obviously, it is minus 1.06 and then 1 and 0. The output will be 0.14457. Now this is the left area of 67. You can see that this is also 67 and it is greater than, right? It's greater than the critical region because the critical region has the probability of 0.025. That means 67 lies outside the critical region. Like suppose the critical region is right here. Well, 67 is here. See, it's outside the critical region. When our test statistic is outside the critical region, we have to accept H0. That means there is insufficient evidence to reject H0. So that means we are going to accept H0. And this H0 is what Gemini's claim in the first place. So we can say that there is insufficient evidence against Gemini's claim. That's it. In question 6, first explain what you understand by the sampling distribution of a statistic. So for the answer, you can just say that it is a probability distribution of the statistic. Next, at Sam's Cafe, a standard breakfast consists of 6 breakfast items. Customers can then choose to upgrade to a medium breakfast by adding 1 extra breakfast item, or they can upgrade to a large breakfast by adding 2 extra breakfast items. Standard, medium, and large breakfasts are sold in the ratio of 6:3:2, respectively. A random sample of 2 customers is taken from customers who have bought a breakfast from Sam's Cafe on a particular day. In question B, we have to find a sampling distribution for the total number of breakfast items bought by these 2 customers. Show you're working clearly. Okay, first let's write down how many items for each type of breakfast. So we have 3 types of breakfast: small, medium, and large. For small breakfast, we have 6 items. And for medium, we have 7. For large, we have 8 items. And now let's see the probability of each of them. The probability of getting small breakfast is, okay, according to this ratio, it is 6 out of, so the total ratio is 11. That is the probability of getting a small breakfast, or the probability of getting 6 items, right? It's the same thing. Okay, now the probability of getting the medium breakfast, which is 3 out of 11. This is a probability of getting medium breakfast, or you can say that it is a probability of getting 7 items for breakfast. And then the probability of getting large breakfast is 2 out of 11, or you can say that this is a probability of getting 8 items for breakfast. Now let's see, we have 2 customers here to consider. They can pick any type of breakfast. So let's find out what are the combinations of the number of items of breakfast that they are going to choose. Because T, our random variable in this case, is the total number of breakfast items from these 2 customers. The first customer could pick 6 items, which is small. And also the second person could pick 6 items. Alright, so that's 6, 6. Or 6, 7 for the second customer. Probably choose medium. Or small and large. Okay, what else? Then the first person could choose medium, which is 7, and small, medium, and medium, or medium and large, which is 8. Well, this one is supposed to be 8 here. And what else? Well, if the first customer chooses large breakfast, well, then the second one chooses small, and so on. This one is like 8, 7, or both of them choose large breakfast. These combinations are still not our T, because T is supposed to be the total number of breakfast items. So let's see the breakfast items here. 6 plus 6, which is 12. That's possibilities of T. We have 12, and 6 plus 7 or 7 plus 6, that is 13. What else? Well, 7 plus 7, which is 14. And then this one can give us 15 and 16. So the possible values for T, which is the total numbers of breakfast items from these two customers, are either 12, 13, 14, 15, or 16. So we got all of the random variables. Now we are going to find the probability for each random variable. Well, the first one is the probability of T equals 12. T comes from the number of items of breakfast. So we have to find a probability from the ratio of each type of breakfast, which is 6 to 3 to 2 here. And in order to get T equals 12, both customers have to choose small breakfast. That means it has to be the probability of small for the first customer, and means you have to multiply the probability of choosing also small breakfast from the second customer. We got the probability of S right here, 6 over 11. So the probability will be 6 over 11 times itself. The answer is 36 over 121. Okay, now move on to the probability of T equals 13. For T equals 13, we have two cases, which are 6 and then 7, and 7 and then 6. So we are going to calculate both cases. Okay, the first one, 6 and 7. 6 means small. That means the probability of small times the probability of 7. 7 means medium. And then we have another case, so we have to keep adding. This is the probability of medium times the probability of small. This is 6 over 11 times 3 over 11. And you have two sets of this. That means you can just simply multiply by 2. And the answer is 36 over 121. Well, next, the probability of T equals 14. In order to get to 14, we have three cases here, 6, 8, 7, 7, and 8, 6. Let's write down the probability of these three cases. The first one, 7, 7, that is the probability of medium times the probability of medium, plus 6, 8, which is probability of small times probability of large. Small, large, and large, small, these two cases, they will have the same set of numbers. So that means you can just multiply by 2. And then we can just put all the numbers here. 3 over 11 times itself, plus 2 times 6 over 11 times 2 over 11. And the answer is 33 over 121. Now we're going to move on to T equals 15. Probability of T equals 15. The case of 15, we have two cases, which are 7, 8, and 8, 7, which is probability of medium times probability of large. And another case is large and medium, which you can just multiply by 2. This one is going to be 3 over 11 times 2 over 11 times 2. And the answer is 12 over 121. Here's come to the last one. Probability of T equals 16, which we have only one case, just 8 and 8. That means it is a probability of large times probability of large, which is 2 over 11 times 2 over 11. It is 4 over 121. Now we can form the distribution table for T. Like this, and that's the answer of part B. Here's come to part C. We have to find the expected value of T. We can find the expected value of T from the distribution we've got earlier. So ET will be 12 times 36 over 121 plus 13 times 36 over 121 plus 14 times its probability, which is 33 over 121, and so on, 15 and 16, 4 over 121. And it will be 146 over 11, which we can round it to 13.3. That's it. Here's the last question. The sides of a square are each of length L centimeters, and its area is A centimeter squared. Given that A is uniformly distributed on the interval 10 to 30, find the probability of L that is greater than or equal 4.5. We're going to start with the distribution of area. So in this case, area has uniform distribution. Start from 10 centimeters squared to 30 centimeters squared. And this is the area of a square of length L. So we can rewrite A as L squared, which is the area of a square that also has uniform distribution from 10 to 30. Well, from this information, we can find the probability distribution from this uniform distribution, which is if A is uniform from 10 to 30, then FA will be 1 over 30 minus 10, which is 1 over 20. Now in this question, we wanted to find a probability that L is greater than or equal 4.5. In this case, we don't have the distribution of L, but we do have the differentiation of L squared. So we're going to use the distribution of L squared instead, which is the probability of L squared is still greater than or equals 4.5 squared. And you can rewrite this one as a probability of A, because L squared is A, which is greater than or equal 20.25. We can draw the distribution graph for this, well, just to make sure how to find the probability of this uniform continuous distribution. First, the distribution starts from 10 to 30 with some probability right here, but we still don't know what is this. And it starts from 10 to 30. We have to find a probability that A is greater than or equals 20.25, which means this area. We can find a probability from the ratios of areas on the graph, which are this small rectangle and this big rectangle. And the area of each rectangle is width times height. But since the two rectangles, they have the same height, instead of finding the ratios of areas, we can find the ratio of width. Start with the one that we wanted, which is the width of the smaller rectangle. That would be 30 minus 20.25, and divide by the whole width, which is the width of the big rectangle, which is 30 minus 10. And the answer is 0.4875. In part B, we have to find the variance of L. Here's the variance formula. E of L squared minus E of L and then squared. First of all, we have to find E of L squared. And we know that E of L squared is E of A. Since A has uniform distribution from 10 to 30, so now EA is 30 plus 10 divided by 2, which is 20. That's E of L squared. Next, we're going to find E of L and then squared. So first, we have to find what is EL. We're going to make this related to A according to the distribution of A that we have here. We know that L squared is A. That means L is square root A. So to find E of L, it's the same as finding E of square root A. Now let's talk about the formula of EX, which is the integration from negative infinity to infinity of x times fx dx. In this case, we wanted to find E of L, which is E of square root A. Well, to find E of square root A, it's the same as when you find E of x squared. And to find E of x squared, it is integration from negative infinity to infinity of x squared itself, but you still multiply with fx and dx. Now you can see that in finding EX squared, everything is the same, but this part is same as this one. If you find E of square root A, you will have to integrate square root A of fa dA. So you still have to stick with function A. And since A starts from 10 to 30, that's going to be the upper and lower limits here, 10 and 30. Now we can put the integration right here and start to integrate it. A to the power of 1/2 times fa, which is 1 over 20 dA. And continue integrating this. I'm going to have 1 over 20, factorize it out, 10, 30, a 1/2 dA. Well, this one will be a to the power of 3 over 2 times 2/3 here. Now we can factorize 2/3 out, and this will be 1 over 30. 30 to the power of 3 over 2 minus 10 to the power of 3 over 2, which is 4.423133. So we already got both values. Now we can find the variance. E of L squared is 20 minus 4.423133. That's EL. So you have to square it here to be E of L squared. And the answer is 0.4358, which we can round it to three significant figures, 0.436. That's the answer.